Okay, let's look at Chapter 4 here. The Bobot can be programmed to perform a variety of maneuvers. The maneuvers programming techniques introduced in this chapter will be reused in later chapters. The only difference is that in this chapter the Bobot will blindly perform the maneuvers. In later chapters, the Bobot will perform similar maneuvers in response to conditions it detects with sensors. This chapter also introduces ways to tune and calibrate the Bobot's navigation. Included are techniques to straighten the Bobot's forward drive, more precise turns, and calculate distances. Alright, so the activities here. Activity 1, program the Bobot to perform the basic maneuvers: forward, backward, rotate left, rotate right, and pivoting turns. Activity 2, tune the maneuvers from Activity 1 so that they are more precise. Activity 3, use math to calculate the number of pulses to make the Bobot travel a predetermined distance. Activity 4, instead of programming the Bobot to make abrupt starts and stops, write a program that makes the Bobot gradually accelerate into and decelerate out of maneuvers. Activity 5, write subroutines to perform the basic maneuvers so that each subroutine can be used over and over again in a program. In Activity 6, record complex maneuvers in the Basic Stamps module, unused program memory to write programs that play back these maneuvers. Okay, so let's look at a few of these. We probably won't get to all of them. Alright, Activity 1, Basic Bobot Maneuvers. Figure 4.1 shows your Bobot's front, back, left, and right. When the Bobot goes forward in the picture, it would have to roll to the right edge of the page. Backward would be towards the left edge of the page. A left turn would make the Bobot ready to drive off the top of the page, and a right turn would have it facing the bottom of the page. Okay, so let's look at that. Alright, so here we have the arrow showing us forward going towards the right of the page. Left turn would go top, right turn would go bottom, and then the backwards, of course, towards the left side of the page, like it said. Okay, remember the front on the Bobot has the prototyping area, and the back has got the single wheel that is just used for balance, the third wheel. Okay, moving forward, here's a funny thing. To make the Bobot go forward, the Bobot's left wheel has to turn counterclockwise, but its right wheel has to turn clockwise. If you haven't already grasped this, take a look at Figure 4.2. Okay, here's Figure 4.2 over here. See if you can convince yourself that's true. Viewed from the left, the wheel has to turn counterclockwise for the Bobot to move forward. Viewed from the right, the wheel has to turn clockwise for the Bobot to move forward. Okay, so on the left here, again, see the wheel in the back here. So forward would be towards the left side of the page. The wheel has to go counterclockwise to push towards the back, making it go forward towards the left side of the page. And here's the right view. Again, the wheel in the back, so it's facing the right side of the page. The front's towards the right side. So the wheel would have to go towards the left in order to get it to go towards the right side of the page. So it would be going clockwise rather than counterclockwise. And that's just because, you know, the motors or the servos are mounted on the other side, opposite sides of the chassis. Okay, remember from Chapter 2 that the pulse out command's duration argument controls the speed and direction of servo turns. The start value and end value arguments of the for next loop control the number of pulses that are delivered. Since each pulse takes the same amount of time, the end value argument also controls the amount of time the servo turns. Here's an example program that will make the Bobot roll forward for about 3 seconds. Okay, so they send a frequency out for the start of the program. There's a speaker connected to pin 4. And then they go through this loop 122 times, 1 to 122. And they just send the 850 and 650 pulse out to the respective pin 13 and pin 12s. So 850, I think that might have been counterclockwise full speed, and 650 might have been clockwise full speed. So that's going to have it go in one direction, I guess forward. So let's look at this. Alright, so this explains what we just looked at. From Chapter 2, you already have lots of experience with the elements of this program. A variable declaration, a for next loop pulse out command with pin and duration arguments, and a pause commands. Here's a review of what each does and how it relates to the servo's motion. Alright, first a variable is declared that will be used in the for next loop. Alright, so this variable here, you see the keyword var again, it's got the name counter, and the amount of, or the size of it is a word, so that can hold 1 to 65,000 for values. Okay, you should recognize this next command. It generates a tone to signal the start of the program. It will be used in all programs that run the servos. So yeah, we have the freak out command to pin 4. Okay. This for next loop sends 122 sets of pulses to the servo, one each to pin 13 and pin 12, and then pausing for 20 milliseconds after each set, and then returning to the top of the loop. Okay. The pulse out 13 of 850 causes the left servo to rotate counterclockwise, while pulse out 12 650 causes the right servo to rotate clockwise. Therefore, both wheels will be turning towards the front end of the Bobot, causing it to drive forward. It takes about 3 seconds for the for next loop to execute 122 times. So the Bobot drives forward for about 3 seconds. I'm not exactly sure why it's exactly 122. The pause of 20 milliseconds, there would be 50 of those in a second, so it would be approximately 150 to be 3 seconds. There is a little bit extra time here, 3 extra milliseconds. Maybe that's what causes it to only be 122 times. Right, the pulse out duration arguments of 650 and 850 cause the servos to rotate near their maximum speed. By bringing each of the pulse out duration arguments closer to the stay still value of 750, let's call that the brake value, you can slow down your Bobot. Modify your program with the pulse out commands. So change it from 850 to 780 and from 650 to 720. So that should make the Bobot move slower. Alright, moving backwards, rotating, and pivoting. All it takes to get other motions out of the Bobot are different combinations of the pulse out duration arguments. For example, these two pulse out commands can be used to make your Bobot go backwards. So we would take that program that we had before and just change the two pulse out lines, and this one would literally be swapping the duration values for the pins. So instead of being 850 on 13, we'll do 650, and instead of being 650 on 12, we would do 850 on 12, and that should have it go backwards. Alright, these two commands will make your Bobot rotate in a left turn, counterclockwise, as you were looking at from above. Okay, so in this case, we do both 650s on both pins, and that would have one wheel go backwards and one wheel go forward. So that's going to be a tight pivot actually around the center of the Bobot, which is actually a pretty cool turn. It's something that you don't see in a normal car. Normal car, you know, both wheels always go the same direction. In our Bobot here, one wheel can go forward and one wheel can go backward at the same time, causing it to do a tight pivot, which is kind of neat. Alright, these two commands will make your Bobot rotate to the right. Okay, it's the same thing as left. We just use 850 for both pins or both servos, 13 and 12. and it will pivot again around the center to the right. Okay, you can combine all these commands into a single program that makes the Bobot move forward, turn left, turn right, and then move backwards. Here's a forward, left, right, backwards dot basic stamp 2. Alright, so it's pretty typical. We have our counter variable here that holds the word size or values 1 through 65,000. That will be used for our loops. We have the start of program signal using the freak out on pin 4 to the speaker. Then we have our forward loop here. It's going to run for approximately a second and a half. And the values on both servos to make it go forward. We have an even shorter amount, which apparently is a quarter turn to the left. So we use 650 on both servos to go to the left. Another short quarter turn to the right using 850 on both servos, and then backwards. And a fifth of a second pause in between these. And here is the backwards on both servos. And backwards again will be about a second and a half. So this going from top to bottom, we would do forward for a second and a half, a left turn for a quarter turn, right turn for a quarter turn, probably in place, and then backwards. So the Bobot should come right back to where it started. Would have gone forward, pivoted left, pivoted right, and then come right back to where it started, hopefully. Alright, so it says your turn, pivoting. You can make a Bobot turn by pivoting around one wheel. The trick is to keep one wheel still while the other rotates. For example, if you keep the left wheel still and make the right wheel turn clockwise or forward, the Bobot will pivot around the left. Okay, so before we weren't using the stop signal, we were actually using back on one wheel and then forward on another. So, and that was turning it right around the center of the Bobot. This is going to be more like how a car would turn. One wheel will be moving much slower. In fact, we're going to keep one wheel stopped here. And then the other wheel is going to push on the outside. So that's going to pivot around the stopped wheel. Alright, if you want to pivot forward and right, simply stop the right wheel and make the left wheel turn counterclockwise. Okay, so same thing in the other direction. These are pulse out commands for pivoting backwards and to the right. Okay, that's kind of interesting. You can actually pivot backwards in the Bobot, which is, I guess, kind of the same as turning while going in reverse in a car. Alright. Activity 2, turning the basic maneuvers. Imagine writing a program that instructs the Bobots to travel full speed forward for 15 seconds. What if the Bobot curves slightly to the left or to the right during its travel, when it's supposed to be traveling straight ahead? There is no need to take a Bobot back apart and readjust the servos with a screwdriver to fix this. You can simply adjust the program slightly to get both Bobot wheels traveling at the same speed. While the screwdriver approach would be called a hardware adjustment, the programming approach is called a software adjustment. Okay, so it's pointing out a pretty common thing you would find in embedded engineering, and that's it's easier to change the software than to change the hardware. Alright, straightening the Bobot's path. The first step to examine your Bobot's travel for long enough is to examine your Bobot's travel for long enough to find out if it's curving either to the left or to the right when it's supposed to be going straight ahead. 10 seconds of forward travel should be enough. This can be accomplished with a simple modification to the forward 3 seconds from the previous activity. Right, so basically this is the same as the 3 seconds. They're going to call it 10 seconds, and they're going to change the counter. I think it was like 120 before. Now it's 407, and that should have it go for about 10 seconds forward. I don't think it's necessary that we do this one, actually. If it meanders a little bit to the left or the right, I think that's okay for what we're doing in class. They are probably looking at doing something that's called dead reckoning here, where they would want to have a very, very accurate amount of control on their maneuvers. But it's not necessary if all you're doing is like a roaming robot application with a little collision avoidance. All right. Let's say that the Bobot turns slightly to the left. There are two ways to think about this problem. Either the left wheel is turning too slowly, or the right wheel is turning too quickly. Since the Bobot is already at full speed, speeding up the left wheel isn't going to be practical, but slowing down the right wheel should help remedy the situation. Right, so if it's already pushing one wheel as fast as it can, you can't make that wheel go any faster, so you got to slow one of them down. All right, remember that the servo speed is determined by the pulse out command's duration argument. The closer the duration is to 750, the slower the servo turns. This means you should change the 650 in the command pulse out to something a little closer to 750. All right, if the Bobot is only just a little off, you might do 663. So that will do the trick. So that would be 13 less than 650 because it's getting closer to 750, which would be slowing it down in that direction. And basically they say you can look at this more. Alright, so we can look at this, and if any of them are really severe, we can make some software adjustments, but I just don't really think it's going to be necessary. Alright, so it's tuning the turn. Software adjustments can also be made to get the Bobot to turn to a desired angle, such as 90 degrees. The amount of time the Bobot spends rotating in place determines how far it turns. Because the for next loop controls runtime, you can adjust the for next loop's end value argument to get very close to the turning angle you want. Alright, so here we had our rotate quarter turn, and basically they use 24 pulses in order to get it to turn left quarter turn. So they're saying basically you run that program and see if you need to go a little bit further or a little bit less, and then you just adjust the counter a little bit. Or you could adjust the speeds by changing these values as well. Again, I don't think we need to be that accurate for what we're going to use this stuff for. Alright, let's say that the Bobot turns just about a bit more than 90 degrees. You could try, going to 23 or to 22. And if you're overshooting, right, so it's saying, you can also change the duration to make that a little bit closer. So there's two things you can adjust here. You can adjust your speed and how long you're sending pulses. And that should allow you to kind of fine-tune these things to be more precise. All right, activity 3, calculating distances. In many robotics contests, more precise robotic navigation lends itself to better scores. One popular entry-level robotics contest is called Dead Reckoning. The entire goal of this contest is to make your Bobot go to one or more locations and then return to exactly where it started. Okay. You might remember asking your parents this question over and over again while on your way on vacation destination or relative's house. Are we there yet? Perhaps when you got a little older, you learned division in school. You started watching road signs to see how far it was to the destination city. Next, you checked it on the speedometer of your car. By dividing the speed into the distance, you got a pretty good estimate of the time it would take to get there. You may not have been thinking in these exact terms, but here's the equation you were using. Okay, time is distance divided by speed. So how long is it going to take you to get there? Well, how far are you going and how fast? Okay. So if you're 140 miles away from your destination and you're traveling 70 miles per hour, it's going to take 2 hours to get there. So how long? You're going 140 miles divided by 70 miles an hour. That is 2 hours. All right, you can do the same exercise with the Bobot, except you have control over how far the destination is. Here's the equation you will use. Okay, the servo runtime is the distance over the speed. So how do you get the speed? Well, you got to test for the speed. And how do you get the distance? Well, that's going to be how far you want to go. So, so the easiest way to do this is to set the Bobot next to a ruler and make it travel for 1 second. By measuring how far your Bobot traveled, you will know your Bobot's speed. So that would be probably the maximum speed. And this is probably assuming 0 ramp time and meaning that we don't control, we don't specify how long it takes before it makes it to the maximum speed. It just starts at maximum speed. And also things like, is there something on the surface that's slowing the Bobot down? So there's quite a few assumptions that are kind of built in here. If your ruler has inches, your answer will be in inches per second. All right, if it is centimeter, it'll be in centimeters per second. Again, I'm not sure that we really need to do this one. We can still do a lot of fun exercises without doing precise navigation here. All right. So yeah, basically you would get a ruler for this one, and you would send your Bobot down for a second, and then you would measure how far it went and figure out your speed, your maximum speed. So yeah, here's the program. 1 second is about 41 times through the loop. Notice they used the maximums of 850 and 650. Hopefully it doesn't run over the ruler. And then they just measure how far it went. All right. You can also think about the distance you just recorded as your Bobot speed in units per second. Let's say that your Bobot traveled 9 inches. It took 1 second for your Bobot to travel that far. This means it goes 9 inches per second. Now you can figure out how many seconds your Bobot has to travel to get to a particular distance. Right, so if you wanted to go 90 inches, that would be 10 seconds, right? Or here's an example for 20 inches. So you would divide 20 inches by 9 inches per second, and you would come up with a value of 2.2 seconds in order to get there. And there's a little note here about conversion between centimeters and inches. There's 2.54 centimeters in 1 inch. That's good conversion to kind of put to memory. In Chapter 2, Activity 6, we learned that it takes about 24.6 milliseconds each time the 2 servo pulse outs and 1 pause command are executed. All right, so we pause for 20 milliseconds. And then I guess there's a little bit over a 3 millisecond on average time to do the pulses. Some of the pulses are a little bit longer than 1.5 milliseconds, and there's a little bit of time starting and stopping those by the basic stamp, a little processing time in there. The reciprocal of this value is the number of pulses per second that the loop transmits to each servo. A reciprocal is when you swap the fractions numerator and denominator. Another way to take the reciprocal is to divide the number of fraction into the number 1. In other words, you divide 1 by 0.024 to come up with 40.65 pulses per second. Okay, so that's where that number 40, did they use 41 or 42? Back 41 here. All right, since you know about the amount of time you want your Bobot to move forward and the number of pulses the basic stamp sends to each servo, you can use these values to calculate how many pulses to send to the servos. This is the number you'll have to use in the for next loops and value argument. Right, so some good examples of practical math here, practical math skills, using your multiplication and division here in order to figure out, well, okay, how far do we want to go? How long is that going to be? And how long that is going to be to run those servos? Well, how many pulses is that going to be? We're going to have to use some multiplication and division to get there. This really isn't all that important again for this class, but it is good to look at. All right, so here's just that example of going 20 inches based on our measurement of 9 inches per second. We get 90 pulses out of that. Okay, activity 4, maneuvers ramping. Ramping is a way to gradually increase or decrease the speed of the servos instead of abruptly starting or stopping. This technique can increase the life expectancy of both your Bobot's batteries and your servos. Okay, and it also keeps it from jerking around. This is probably the preferred way of doing navigation really, but it's going to mess up our calculations. So what's going to happen is we're going to start off slow and we're going to allow those servos to ramp up in their speed as we're going along, but that is going to wreak havoc with our dead reckoning exercises, our calculations that are based on a constant amount of speed, because these the way we're going to move the Bobot using this ramping is going to vary the speed until we build up to full power. So like I was saying in the last chapter, the last section, using the dead reckoning or the calculating distance, isn't maybe so important, as we'll probably be using this idea of ramping instead. All right, programming for ramping. The key to ramping is to use variables along with constants for the pulse out command's duration arguments. It must be instead. Figure 4.4 shows a for next loop that can ramp the Bobot's speed from full stop to full speed ahead. Each time the for next loop repeats itself, the pulse out count variable is increased by 1. The first time through, pulse out count is 1, so like using the commands pulse out 13, 751, and the pulse out 12 of 749. So it's 1 greater than 750 and 1 less than 750. All right, the second time through the loop, the pulse count is 2. So it's like using the pulse out command 752, or 2 more than 750, and 748, 2 in the other direction. As the value of the pulse out pulse count variable increases, so does the speed of the servos. By the 100th time through the loop, the pulse out variable is 100, so it's like using 850 and 650. And so now you can see that this is actually like a power level. So power level 1 is barely moving from that stop value of 750, because it's just 1 more or 1 less than the stop value. And power level 100 is 100%, or 100 more than 750, or 100 less than 750, depending on the direction you're going. So you can think of it as the power level, and we're just going to slowly move from power level 1 to power level 100 in order to start our maneuvers. And so it's saying, yeah, you'll increase your battery life and your servo life, and it'll also keep it from jerking around. Alright, recall from Chapter 2, Activity 5 that the 4 next loops can also count downward from a higher number to a lower number. You can use this to ramp the speed back down again by using for pulse count equals 100 to 1. Okay, so basically if your start value in the for loop is higher than the end value, it will count downward from that start value to the end value. All right, here's an example program that uses the for next loop to ramp up to full speed and then ramp back down. Okay, we have our new variable for pulse count here, size of the word. It does the start frequency here. All right, so we ramp forward here from power level 1 to power level 100. We're going forward full speed for, let's see, almost 2 seconds. And then here's the ramp down here. So the ramp from a power level 100 to 1, and here is where we use those power levels. So we're just going to power back down. So it's going to start off slow, get fast, then it's going to run at full speed for a while, and then it is going to slow back down. Okay, so it says your turn. You can also create routines to combine ramping up or down with other maneuvers. Here's an example of how the ramp up to full speed going backwards instead of forwards. The only difference between this routine and the forward ramping routine is that the value of the pulse out count is subtracted from 715 in pin 13 command where it was added, right? So all what it did was basically change the direction of each of your servos compared to the stop value. All right. You can also make a routine for ramping into a turn by adding the value of pulse count to 750 in both pulse out command by subtracting pulse out. The servos don't get an opportunity to get up to full speed before they have to slow back down again. Alright, so yeah, so this is a ramp right routine. Interestingly, they start at 0 for the power level here, and they only go up to 30, so it's going to be a slow turn to the right. And here's a ramp down portion of turning to the right. Again, it only ever gets up to power level 30 and then back down. Alright, activity 5, simplify navigation with subroutines. Alright, in this next chapter, your Bobot will have to perform maneuvers to avoid obstacles. One of the key ingredients to avoiding obstacles is executing pre-programmed maneuvers. One way of executing pre-programmed maneuvers is with subroutines. Okay, so new software for basic stamp here, anyways, for people is the use of subroutines. So this is going to be important. We'll use this in later activities. This activity introduces subroutines and also 2 different approaches to creating reusable maneuvers with subroutines. Alright, inside the subroutine, there are 2 parts of the basic subroutine. One part is the subroutine call. It is a command in the program that tells it to jump to the reusable part of the code, then come back when it's done. The other part is the actual subroutine. Alright, it starts with a label that serves as the name and ends with a return command. The commands between the label and the return command make up the code block that does the job you want the subroutine to do. Alright, figure 4.5 shows part of the PBasic program that contains the subroutine call and a subroutine. The subroutine call is go sub my subroutine. Alright, so go sub is the command. You'll see that whenever you want to call subroutine, and then my underscore subroutine is the name of your actual subroutine. So we'll see that. Alright, the actual subroutine is everything from the my subroutine label through the return command. Alright, so in order to specify a subroutine, all you do is you put the name in a colon, and then the only requirement is once you get to the end, you just do a return. Alright, here's how it works. When the program gets to the go subroutine in the subroutine name command, it looks for that label. So as it's seeing your code and it sees this line where it says go sub and then it sees this name at the end with my subroutine, it's going to look for the my subroutine with the colon label. Alright, as shown by arrow 1, the program jumps to my subroutine and then starts executing commands. The program keeps going down line by line from label, so you'll see the message command in subroutine. Alright, so it's kind of hard to explain with words. It's probably a little bit better with these arrows. Alright, so in our normal program here, we'd be going top to bottom. This just happens to be in a do loop here. They print out some debug saying, you know, we were here before the subroutine so that you can see where we were, and then they pause for a second, and then they call. They say go my subroutine. That's what I would call a calling of the subroutine, which causes the flow of execution to go here. So the next thing isn't after subroutine, but it's actually the code inside the subroutine itself. So when it sees that goes sub, instead of doing the next line after it, it jumps down to the label for the subroutine. Alright, so the next thing you should see in your terminal should be this command in subroutine, and then it would pause for a second before coming back to the place where it was called from, and then you would have this after subroutine print out to the console, and then it would be doing that over and over again. And so the idea here is that rather than writing things out over and over and over again in your main program, you can make a routine that can be called many times in your main program. And so if that routine is large or complicated, you can make it's much easier just to get it right once and just call that routine over and over again rather than trying to re-implement that logic over and over again. Alright, I hope that made sense. Alright, so here is their example program for that. It's basically what we just saw. Again, you just put in a name with a colon for a label. That tells it that it's going to be a subroutine. You do a return at the end of it. The commands inside of it are the debug command and the pause command. This is our normal program. We hit this go sub with the name, tells it to jump there. So we can have many of these routines where it's name with a colon, and then you can call each individually by the go sub command, giving them their name. So we'll see some examples of that. Alright, in fact here's one with two subroutines. One subroutine makes a high-pitched tone while the other makes a low-pitched tone. Alright, so these are going to use the speaker as examples. Alright, so here's our main program. It's got a main loop. It's just going to run this over and over again. So it says call the subroutine high pitch. There's going to give some debug saying that's back in the main loop. Then it says go subroutine low pitch. It's going to call low pitch after 1 second, and then it'll print again that it's back in the main loop when it's done, and this is just going to tell you that the main loop is repeating. Okay, so from the high pitch, it's going to come in, it's going to print out that it's in high pitch, and then you're going to hear through the speaker, it's going to combine a 2K and 3.5K signal mixed, or maybe that's actually a 2K for 3 seconds. Can't remember exactly how that worked. And then we would come back through, and then we would call the low pitch being, I'm thinking this is 2 seconds now, a 2 second with a 2K. So this is going to be a 3.5K sound, and this is going to be a 2K sound with 2 seconds. Alright. Alright, now it says let's try putting that together with forward, left, right, and backward navigation routines inside subroutines. Okay, so movements with subroutines, basic stamp 2. Here's the program. Now, if you look at our main portion of the program, it's become incredibly simplified here. So we have our 3K start of program signal that lasts apparently 2 seconds, and then it says go forward, go left, go right, go backwards. So that's it. That's our main program, and you can build up more complicated procedures just by using these go subs. And it should look somewhat like as if you're doing like the Osmo programming, where you're just kind of grabbing these basic commands and starting them top to bottom. And there's actually an end here for the end of the program. So that tells the basic stamp to go into low power mode when it's done. Now, after the end of the program, we can still declare our subroutines. So we have the subroutine forward here. Remember, it's just the name with the colon in order to create a label, and then it has return at the end. Okay, so we know how to do forward, right? This looks like forward for 2 seconds, maybe, or a second and a half forward. Our normal counterclockwise and clockwise on our 2 servos with the normal pause. There is a pause at the end of it. Here's our left subroutine. This was, I believe, the quarter turn length. Remember, one wheel's going forward and the other going backward, so it's going to pivot around the center. Same thing with right, it's just that we're using the other direction for our servos. And backwards. So backwards, all we've done is flipped the direction of the 2 servos here compared to forward. Instead of 850 and 650, it's 650 and 850 respectively, and again a second and a half. Okay, so you could put in multiple forwards here. You could go sub forward, 3 or 4 times in a row. Then you could do a left. Then you could do some more forwards, which would actually be moving left compared to its original position, and so on. So I hope that makes sense, and I hope it shows how much utility you can get out of those subroutines. Alright, you should recognize the pattern of movement your Bobot makes. It is the same one made by forward, left, right. Alright, clearly there are many different ways to structure the program that will result in safe movements. A third approach is given an example below. Alright, here's another example program that causes your Bobot to perform the same maneuvers, but it only uses one subroutine and some variables to do it. You have surely noticed that up to this point, each Bobot maneuver has been accomplished with similar code blocks. Compare these 2 snippets. All right, we have forward full speed versus ramp down full speed. Okay, so all right, we have our forward for 1.5 seconds at the full speeds of 850 and 650 versus our ramp. So our ramp goes from, this is ramp down actually, we ramp down from power level 100 to power level 1, where that is calculated compared to the stop duration. All right, what causes these two code blocks to perform different maneuvers are changes to the start value and end value arguments and to the pulse out's duration arguments. Right, so we can see that here's the start value of 1 to 64 versus a start value of 100 down to 1. So that's, implying a different direction in how we count through that loop. And then the duration for the pulse outs are different here. We have full speeds in one example, and they're constant in their direction, versus an offset, or an offset based on the power level from the stop position. Okay. You could actually really get fancy and control the directions individual inside there. All right. Let's see. These arguments can be variables, and these variables can be changed repeatedly during the program runtime to generate different maneuvers. Instead of using separate subroutines with specific pulse out duration arguments for each maneuver, the program below uses the same subroutine over and over. The key to making different maneuvers is to set the variables to the correct values for the maneuver you want before calling the subroutine. Okay. All right, so this one's going to be called movement with variables and one subroutine. Okay, so it looks like we have more variables here. We have our counter variable. We have a pulse left and a pulse right and a pulse count. Okay, so our typical 3K starting frequency here. We have here's the example for forward. Okay, so it says we're going to use our pulse left is going to be 850, our pulse right is going to be 650, and then we are going to do a count of 64, and then the subroutine is called navigate, so it just calls navigate. So it sets up those three variables and calls the navigate routine. So that means the left servo is going to be sent 850s. I think that was full speed counterclockwise, and the right was 650s, which I think was full speed clockwise. And then this is going to be 1.5 seconds. So it's going to set up those things, and it's going to call navigate, and that's going to be a forward. Okay, so a left turn example here. We do a pulse left. The left servo is going to get a 650. The right servo is also going to get 650. So one's going to turn forward, the other's going to turn backwards. I guess the left is going to go backwards, the right's going to go forwards. And our pulse count 24, well, that's what we use for 1/4 of a turn. So when we call navigate, it'll do that. All right, right turn example, set up pulse left to be 850, pulse right to be 850. So notice that it's the opposite side from a left turn, the opposite values, the opposite side from 750. Rather than being 100 power level less, it's 100 power level more than 750. And the same duration, and so that's going to cause it to go right. All right, so backwards. All we should have different compared to forward is the direction on both the left and right servos. Okay. So that's forward, left, right, back, and then the program is over. So here's the navigate routine. Navigate, we're just going to go through the for loop that we've seen over and over again. based on that variable that we set each time, which is the pulse count. So for forward and backward, it's going to be 64, which is a second and a half. For left and right, it's going to be 24, which was a quarter of a turn. Okay. And then we just send that value that we specify to each servo, pulse left and pulse right here. So for example, for backwards, you had a pulse left for 650, so that 650 would be put in here. Pulse right of 850, so 850 would be put in here. So I hope that makes sense. These three variables control the navigate routine. So variables, work by substitution. So we have pulse count being 64 for this call. So this would be a replace of 64. So the loop would run from 1 to 64. Pulse right would be 850. So that would be substituted into 850 here for this call to navigate. And pulse left of 650, when we call navigate here, that value would be put here. All right, so that's how subroutines work in this basic stamp language. It's a little different from other programming languages, and it's not quite as clean, but I kind of hope that explanation made sense. Did your Bobot perform the familiar forward, left, right, back sequence? This program may be difficult to read at first because the instructions are arranged in a new way. Instead of having each variable statement and each go subcommand on a different line, they are grouped together on the same line and separated by colons. I didn't even notice that. Apparently in Basic Stamp you can put more than one command on a line, but you have to put colons in between them, which don't confuse that with a label. Here the colons function the same as a carriage return to separate each P basic stamp instruction. Using colons this way allows all the new variable values for a given maneuver to be stored together on the same line in the subroutine call. Okay. All right. This activity 6, you can read over that if you'd like to. Basically, you can put things into the EEPROM such that the maneuvers can be replayed out of the memory on the basic stamp. This is very much an advanced topic, but it can be interesting if you have time to go through it. And I think that's basically going to be it for this chapter.